So the instructions will remain the same. We will start at 3 p.m. and in case of any doubts and queries, you can type it in the chat box. Right now we have only one participant. I hope some others join. I think we can start. So let's just start. Let me just share my screen first. So we are bound to give this introduction every time. So good afternoon, everyone. My name is Musab Rafiq. I'm a course TA for this course on digital circuits that is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. Myself, I'm a PhD student at IIT Kanpur in the Department of Electrical Engineering. This is live session number 9, where we are going to solve problems related to week 9 tutorial. And let me just begin with the first problem of today's live session. So the first problem of today's live session is: each cell of a static SRAM cell contains A option A 6 MOS transistors, that is metal oxide semiconductor transistor, B 4 MOS transistors and 2 capacitors, C 4 MOS transistors, and option D 2 MOS transistors. So yeah, I'm just recording, so it's for this recording is also available. So if you can just let me give the answer, that will be fine. Other than that, you can type in your answers. So this each cell of static SRAM cell contains 6 MOS transistors, as rightly said by one of the participants. It contains 6 MOS transistors. So I would like to give some brief overview of this SRAM cell. So this is a 60 SRAM cell, as you can see. This 60 SRAM cell consists of a cross-coupled inverter pair that forms a bistable element. So here M1, transistor M1, M2, M3 and M4, they form a cross-coupled inverter pair. So what is the cross-coupled inverter pair? You can see the input of this is basically output of one inverter, which is again connected to the input of this inverter pair. So we can just draw it like this. The cluster of this M1, M2, M3 and M4. M1, M2 form one inverter and M2, M3 and M4 form one inverter. So this simply can be represented like this. this is your cross-coupled inverter pair, which also formed as bistable element. So the output of this goes to the input of this, and the output of this goes to the input of this. As you can see, this here is the input, and this here is the output, which goes to the input of this inverter, and the output of this inverter goes to the input of this inverter. And the transistor M5 and M6, they form the excess transistors. They are also called excess transistors. So I'll just give the brief overview of how read and write operation occur in this. So these bit lines, what we do is we let us assume that we read operation we will discuss first, as we have a 1 at q, and so q bar will be 0. So once q bar is 0, that implies we will have, for a read operation, these bit lines are pre-charged to some voltage, both bit line and bit line complement, and this word line is asserted high. As this word line is asserted high, what happens? If this q was equal to 1, that implies q bar is equal to 0, and the voltage at this will be grounded using this, will be connected to this node via this transistor M5, and this M1 will pull down this voltage to ground, and as a result, BL bar voltage will change from some pre-charged voltage to 0, while for the BL it will remain unchanged. And if one was if 0 was q was stored as 0 and q bar would have been 1, BL bar would have remained the same, no change on BL bar voltage, and at BL the voltage would have been pulled down to ground. So this is how the read operation is carried out, and the write operation will be done from this end, where this word line will be asserted high, and whatever voltage we want to store, it will be given via this bit line. We have this concept of this sag ratio and pull down ratio. I think we will not cover that thing in this part, because it is mostly the problem solving session. So also I would like to give some this thing that we have some other configurations of SRAM cell, like 8T SRAM cell, where 8 transistors are used, and in that case read and write paths are decoupled. So this was something I just wanted to point out. This was this main point. This was a cross-coupled inverter pair, which is composed of this M1, M2, M3 transistors. These are your excess transistors, and we have this thing called sag ratio and pull-down ratio, which we will not be covering in this live session. You can refer to some textbooks to get an idea. Simply sag ratio means this pull-down strength of this transistor is greater than this, and pull-up ratio means that this strength is greater than this strength. That's simply, so it's related to the sizing constraints of the transistor. So if you had any doubts regarding this, you can type in chat box. There's only one participant, so I think we can use this mic system also. So Dr. Das, I hope this was clear. Okay, we can proceed now. Okay, so there are no doubts, so we can proceed to the question number 2. So question number 2 asks us, which of the following statement is true? So out of the 4 statement, only one of the statement is true. So we have the statement, assessing any memory location of RAM takes same amount of time. Assessing any memory location of sequential access memory takes same amount of time. Low cost memory can be designed using SRAM cells, and SRAM memories need a periodic refreshing circuit. So it's a pretty much straightforward answer. We know that for to access any memory location in RAM, it takes the same amount of time. And SRAM memory cell, they don't require a periodic refreshing circuit. They are volatile memory, means they constantly need power supply, and the transistors are used to store the information. And low cost memories cannot be designed using SRAM cells. They are pretty much expensive. So this was a pretty much theory question. So I think we can proceed to question number 3. So this is again a theoretical question. It states that which of the following statement is true? Hamming can could detect 2 errors. Hamming code with extra parity bit can detect 2 bit errors. Hamming code can detect 2 errors present in the corrupted data word. Hamming code can detect and correct a single bit error only. So the answer is, as we know, this Hamming code is used to detect and correct a single bit error only. Now, again, moving forward to this question number 4, which is based on this PLA. So, for the given circuit, identify the question answers. For the given circuit, identify the outputs A. So, these are your outputs A, output A, and output B. We are given this circuit, and we need to find out this output of this NOR X OR gates, and these X indicates the connection. So, what we will do is, we will first mark down these points. Let's just mark down by some A, B, C, E, and E. So this A, here we have this X, and this line represents X complement, this represents Y, and this line represents Y complement. This line represents Z, and this line represents Z complement. So we'll just write down here, this A is simply equal to, what is this A equal to? This A is equal to X and Y. So this A is equal to X and Y, small a, this is small a. Then we have this small b. This small b is again equal to x and z complement. So this small b will be equal to x and with z complement. Then we have this c, which is again equal to the same thing, x z complement. Then we have this d. D is equal to x, if we can see from this, and y complement, x and y complement. And then we have this e, which is equal to y and z. This is y and z. Now our final output, which is the capital A and B, is simply equal to A or B. So this is xy or with xz complement, and my B, output B, is simply equal to C or D or E. So this thing is equal to xz complement plus xy complement plus yz. So if we carefully look our options, this is xy complement, so it won't be here, xy plus xz bar, which is A, and B is our xz bar plus xy bar plus yz. So this is option B. So for this given circuit, our outputs are A equal to xy plus xz bar, B equal to xz bar plus xy bar plus yz. So if there are any doubts, please type it in the chat box. Question 3, last option. Last option. You want me to repeat question 3? Okay. So this question 4 was clear, huh? So Hamming code can detect and correct only single bit error only. So we can only detect one error using Hamming bit. So if there are two errors present in the code, we can't detect using Hamming code. If only one error is there, we can detect it and then we can correct it. This is the only option that was true among these. Now there was no doubts in this, I assume. So there are no doubts in this. We can move forward to this question number 5. So question number 5 asks us, a programmable logical array can be used as a microprocessor, as a dynamic memory to realize a sequential logic and to realize a combination logic. This is a pretty straightforward question, and we have done so many questions on this thing. We know that a PLA can be used to simply realize a combination logic, as just we saw right now. So let me just check if there are any participants. So it's clear till now. Okay, that's fine. So let me just move to the next question. That is question number 6. Where I am. Oh, so the minimum number of transistors required. So the question asks us the minimum number of transistors required to make a dynamic RAM cell is. So dynamic RAM, often short, we call it as DRAM. So the question asks us the minimum number of transistors required to make a DRAM cell is option A 1, option B 2, option C 3, and option 4 4. So 1, 2, 3, 4 sequential options. So as you know, minimum number of transistors required to make a DRAM cell is A1. In a 1T 1C structure, we only use one transistor to achieve a DRAM cell. So this, I'll just give some brief introduction to this part. So the question asks us the minimum number of transistors. We have a structure, a 3T DRAM cell, where the 3 transistors and 1 capacitor are used as a memory element. So this is termed as 3T DRAM cell. Information is stored on the capacitor, this capacitor. So this was the first industrialized DRAM in 1970s. So how does it work? So if you want to, first we will discuss the write operation. If you want to store the data, what we will do, we will assert the word line WWL. It's known as write word line. We will assert the word line high. Asserting means we'll just give some voltage to it and just turn it on. And because of the voltage present on this write word line, this M1 transistor turned on. And whatever value we want to store, we will just put it on this bit line 1. So as this transistor M1 is turned on, this value gets stored on this transistor CS. So after this write operation, we will have the read operation. So for a read operation, we will assert our read word line, assert our read word line high. So as the read word line goes high, this M3 transistor is turned on. And based on the value stored at this CS capacitor, this M2 transistor will be turned on and turned off. So if and also we'll precharge this bit line. So if 1 was stored on this transistor, the capacitor present in this will get discharged through this M2. So when CS is high, CS high means if VDD was there, or here the voltage here, we'll just call it this VO, VO will turn to 0. And if the CS was 0, our VO will remain as high. That is high means VDD in bracket will call it 1. So it is an inverse of whatever was stored here. So if 0 was stored here, this will remain at high. If 1 was stored here, this will remain as this will go to 0. So it will discharge. So this is how we'll sense our input. It will be basically an inverse of whatever is stored. And also you must be knowing that this DRAM is a dynamic random access memory. It constantly requires a refreshing operation, because as whenever we do a read operation, it leads to the loss of information. So we need to refresh this thing periodically. So refresh means we have to constantly read the, after certain time intervals, we have to read the state and write that state. So refresh means read and write. So there are some intervals after which it's read and written again, because in capacitor we have some losses, charge gets leaked. So we will read the state and then write again. So we have this constant refreshing. And also we have this 1T 1C DRAM cell, which we often call as 1T DRAM cell. Here this only one transistor is used. So first of all, we have this write operation for a 1T 1C cell. Whatever value we want to store, we will put on this CBL, and we will assert the word line hand, and as a result CS gets stored to this. And for a read operation, we will just charge this capacitor to VDD by 2, so to some pre-voltage V pre. And once we assert the word line hand, based on the voltage present at CS, this V pre either gets this V pre, sorry, the voltage at this node, let me just term it as VC. VC will either increase or decrease, so it will be somewhat like this. In the start of the cycle, let's just it was at V pre, And once we started this read operation based on the value stored here at CS, it will either decrease or increase. And also for a 1T 1C, we have a necessity to use a sense amplifier. So it will just base sense amplifier just senses the direction, whether the voltage is increasing or decreasing. So based on that, it will just pull it down to ground, or it will just pull it up to VDD. That's how the operation of 1T 1C is carried out. And here there is a necessity to use a sense amplifier. So this was just a brief introduction to the DRAM. I think this is pretty much sufficient for at this level. And also, if you have any doubts, please type it in the chat box regarding this thing. So is it clear? I hope it's clear. I hope I was clear with my this. Actually, I'm just okay. So let's now move to the next problem of today's session. So the next problem of today's session is find the 12-bit timing code for a 8-bit data. Sorry, 10101100. So we are required to find this 12-bit timing code for a 8-bit data word this. So what we'll do is we'll just create a table like this. This is my way of doing it. You can do it as you wish. We need to find out this P1, P2 parity bits, P1, P2, P3, P4 data bits we have with us 1010 1100. So we'll be using these 4 parity bits and 8 data bits. So in total 12 bit code word. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then we have this 12th bit. So we need to find out these bits 1, 2, 4, and 8. So our D1 is 1, so this will be 0, 1, 0, 1, 1, 0, and 0. So first, so how will we find this P1? So P1 will simply be equal to the XOR of all the bits wherever this one bit is used. So it will be XOR of, so this one bit is used in, uh, if you know this 8421 system, so in case of 00080000, then it is 1, 2 is simply here, 3 is like this. So what I am trying to say, 4 is here, and 3, 5 is here, 4 plus 1. What I'm trying to say, wherever this 1 is right, that number will be used for this XOR sum. So it will be 3, 5, 7, 9, 11. So it will be XOR of 3, 5, 7, 9, 11. That implies it will be XOR of 3 is 1, 5 is 0, 7 is 0, 9 is 1, and 11 is 0. So XOR of 2 ones is 0. So P1 will be 0. Then we have 2, P2. So 2 is here, there in 2 is here in 4 plus 2, 6, 4 plus 2, 6, 6, 7, 4 is 2 is there in 6, 7, and it's also there in 10 and 11. 6, 7, 10, 11, and it's also in 3. 2 plus 1, 3. Yeah, 2 is there. So 3, 6, 7, 10, 11. So XOR of bits present at 3, 6, 7, 10, 11. So it will be XOR of 1, 1, 0, 10 and 11 are 1 and 0. So XOR of 3 ones, 1 and 1 odd number of ones, so it will be 1. Then similarly we have this P3. So P3 is basically this fourth. This is P1, P2, P3 and P4. So P3 will be XOR of wherever this 4 is used. So it will be 5, 6, 7 and 12. 5, 6, 7, 12. So it will be XOR of 0, 1, 0, 0. So it will be 1. And then finally we have this P4 bit. So P4 will be equal to XOR of 8 plus 2 is 8 plus 1 is 9, 10, 11 and 12. So it is XOR of 9, 10, 11, 12. So XOR of 1, 1, 0, 0, 0, 1, 1, 0, 0. XOR of 9, 10, 11, 12. So XOR is 1, 1, 0, 0. So it will be equal to 0. So my P1 is 0, my P2 is 1, and my P3 is 1, and my P4 is 0. So my final code is 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0. So this is option 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0. So this is option B. So it's clear. We can move forward to the next question. So the next question of today's live session is question number 8. So the question number 8 asks us, question number 8 asks us a 12-bit Hamming code read from a memory location. This Hamming code contains 8-bit data and 4-bit code word, as we already saw. What was the original 8-bit data stored in the memory location if the 12-bit Hamming code is this? So we are given this 12-bit Hamming code and we are asked to find the correct code or whatever the code was stored at the original location. So we'll again make these 12 boxes. These boxes just help you, otherwise you can do it as you wish, as per your wish. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So this is, then I will write down my code. So the code is 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0. So we need to find out the error bit, and once we get the error present as bit, then we can get the where this error is present, then we can get the correct answer, a correct original code, original data. So we'll just first find out this C1. So this C1 will be XOR of 1, 3, 5, 7, 9, 11. So this will be XOR of 1, 0, 0, 0, 1 and 1. So 3 ones, it will be 1. Then we have this C2, it will be XOR of 2, 3, 2, 2, 3 and then 2, 3. It will be XOR of 2, 3, 6, 7, 10, 11. 2, 3, 6, 7, 10, 11. So 2 is 1, 3 is 0, 6 is 1, 7 is 0, 10 is 0, and 11 is 1. So odd number of 1, it will be 1. And then we have this C4. So XOR of 4, 5, 6, 7, and 12. 4, 5, 6, 7, and 12. So 4 is 1, 6, 5 is 0, 6 is 1, 7 is 0, and then 12 is 0. So even number of 1, it will be 0. And then we have this C8, it will be XOR of 8, 9, 10, 11, and 12. So it will be 0, 1, 0, 1, 0. So it will be 0. So the error will be present at C8, C4, C2, C1, 0, 0, 1, 1. So error will be present at C2, so error will be present at third bit. So third bit is this. So if it was 0, it will be just 1. Rest all other data bits will remain same. So 1, these are redundant bits. So let me just mark the redundant bits and just write down the data bits after correcting. So this was 0, this now became 1, and all other will be same. 0, 1, 0, 1, 0, 1, 0. So my code will be 1, 0, 1, 0. My original data 1, 0, 1, 0. This is option A. Error was at the third bit, so the value got changed to 1, and all other bits remained the same. So correct data was 1, 0, 1, 0, 1, 0, 1, 0. That is option A. So I think we can proceed to next question. So there are no doubts, we can proceed. So the next question asks us, in Hamming code, how many check bits are required for a data word of 25 bits? So the question asks us to find the number of bits required for data word of 25 bits. So we know this, for this Hamming code, the number of redundant bits or parity bits k, it should satisfy this relation. 2 to power k should be greater or equal to n, where n is the number of bits in the data word, plus k plus 1. So here n is equal to 25. So 2 to power k should be greater or equal to 25 plus k plus 1, and this is equal to 2 to power k should be greater or equal to 26 plus k. So if you give this, we have to give we know this k values will be in integers, positive integers. So if you have k equal to 3, so it will be 2 to the power 3 equal to 8. 8 greater or equal to 8 is greater than 29, which is false. Then 2 to the power 4, it will be 2 raised to the power 4 is 16, greater than 26 plus 4 30, that is false. Then we have this 2 to the power 5 equal to 32. 32 is greater or equal to 26 plus 5, that is 31. So this relation is satisfied. So what is k for k equal to 5? We get 2 to the power 5, that is 32. 32 is greater or equal to 26 plus 5, that is 31. So this relation is satisfied. So we have n equal to 25, k equal to 5. So option B is our correct answer. Now moving forward to the next question, it is again based along the same lines. So the question 6 asks us, what is the size of Hamming code? So we are going to find out the complete size of the Hamming code for a 32-bit data. So in previous question, we were just required to find out the number of bits we will be redundant bits that will be required or parity bits will be required. Now we are doing this 32-bit data word, so we need to find the number of parity bits and tell the total length of the data. So again, we will use the same formula, same condition, that is 2 to the power k should be greater or equal to n plus k plus 1. So k n plus k plus 1. So n is here equal to 32. 32 plus 1 is 33. 33 plus k. So if we just plug in the value of k equal to 5, so 2 to power 5 is equal to 32. 32 is greater or equal to 38, which is false. So if you plug k equal to 6, so 2 to power k, 2 to power 6 is equal to 64 for k equal to 6. 2 to power k 6 is equal to 64, greater or equal to 33 plus 6 is 39. So this thing is satisfied. So for k equal to 6, this thing is satisfied, and so that implies our number of bits will be equal to n plus k, uh, which is equal to 32 plus 6. So my required number of bits are 38. That is option B. Any doubts? Can we proceed? Yeah. So I guess you're typed in. So we can proceed to the next question. The next question asks, which type of memory has a constant of minimum operating block frequency? Number one is EPROM, which is electrically erasable programmable read-only memory. Number two is static RAM, that is SRAM, as we saw earlier. Number three is dynamic RAM, that is DRAM, and the final is magnetic resistor RAM, that is AMA RAM. So we know this in EEPROM we store data by using the electrical pulses and erase data using electrical pulses. In static RAM, it's a volatile memory where power supply is constantly given to store the data on the transistors. In the magnetic resistor RAM, magnetic tapes are used to store the information. But in dynamic RAM, where a capacitor is used, that capacitor is used for storage of data, and that capacitor has leakages, and as a result the charge gets leaked and our information might be lost. So to avoid that information loss, these DRAM are constantly refreshed. So what is refreshing? We are reading the state and then writing the same state. So for that thing we need a clock for that thing, and as a result refreshing clock cycles are required for the retention of data stored. So the correct option to this question is option C, DRAM. Now towards the next question, which is along the same lines, which memory is difficult to interface with processor? So as we saw earlier, we need a constant refreshing for this DRAM. So capacitance charge leakage which require refresh. So due to this refreshing cycle, which is done periodically, it becomes quite difficult to interface the DRAM with processor. Now to the next question, that is question number 13. So what is the Hamming distance between the codes 11001011 and 10001111? So we are given these two codes. Code 1 is 11001011 and C2 is simply 10001111. So Hamming distance, what is Hamming distance? It is basically a metric to compare two binary strings of equal length. So you can see C1 and C2 are same length. So what Hamming distance gives us? It gives us the number of bit position in which the two bit positions are different. So Hamming distance is a metric to compare two bit strings of equal length, and it gives us the number of bit position at which there are different two bit positions are in which two bit positions are different. So get the number of positions at which the two bits are different, we have to simply XOR the two codes. So to get the Hamming distance, we XOR the C1 and C2, and we finally count the number of ones that will give us the Hamming distance. So it is 1101011 XOR with 10000. How many zeros are there? 4, 1, 2, 3, 4 and 3, 1. So we will XOR each bit. So 1 1 is 0, 1 1 is 0. So this is 1, 1 1 is, so this is 1. This is 0 0 0. Oh, this is 1. This is 1. This is 1 and this is 0. So we'll count the number of ones. So number of ones here, number of ones here after XOR operation is 3. So the Hamming code distance between these two code words is equal to 3. So option 2, which is equal to 3, is our correct option. So any doubts? So I'll just show. So first we need to understand what is this Hamming code, Hamming distance, Hamming distance. So Hamming distance is basically a metric between that compares two bit strings of equal length. So you can see they are of equal length. I guess 8 bit, 8 bit length. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So what is Hamming distance gives? It gives us the number. It gives us the number at which the two bit positions are different. Two bit values at two bit positions are different. So how we will get these two number? So we'll take the XOR. So we took the XOR of C1 and C2. And when we do XOR at the individual bit position, so one XOR with 1 is 0, one XOR with 1 is 0, and one XOR with 0 is 1, one XOR with 0 is 1, these two are 0, then one XOR with 0 is 1, and one XOR with 1 is 0. So how many number of ones we got here? We got 3 ones. 1, 2, 3. So at 3 bit positions they are varying. Simply at 3 bit positions they have different values. So that is how the Hamming distance between minimum Hamming distance between them is 3. I hope I was clear. So let me move forward to the last problem of today's session. So this session is again based on this parity code, code. So the final code after encoding data bits 1101 into 7-bit parity code is. So we have data bits equal to 4 and parity bits equal to 3, which satisfies this relation. 2 to the power 3 should be greater or equal to n plus k plus 1. So here n is equal to k is equal to 3. 2 to the power 3 is 8, and 4 plus 3 plus 7 plus 8. So 8 greater or equal to 8 is satisfies the relation. So we are using 3 parity bits. So how we'll do with this? We'll just write down this. We'll just make down this table first. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. These are my parity bits. I will just mark them. My data is 1, 1, 0, 1. So to get this P1, we will take the XOR of 3, 5, and 7. So the XOR of 3, 5, 7 is 1, 1, 1. XOR of 1, 1, and 1, which is equal to 1. Then we have P2, which is simply equal to XOR of 2 plus 1 is 3, 5, 3, 6, and 7. So it is XOR of 1, 0, 1, so it will be 0. And P3 is equal to XOR of which is 5, 6, and 7. That is 1, 0, 1. XOR of 1, 0, 1 is 1. So my P1 is 1, my P2 is 0, and my P3 is 1. So plugging these values 1, 0, 1. P4 is 0. P4 is 0. P4 is 0. This is 0. This is XOR of 1, 0, 1. XOR of 1, 0, 1 is 0. So this is 1, 0, 1, 0, 1, 0, 1, 0, 1. 1, 0, 1, 0, 1, 0, 1. That is option 3. 1 0 1 0 1 0 1. So option 3 is correct answer to this question. So if you have, yeah, 0, yeah, I corrected that. So if you have any doubts regarding the any question, you can just ask me. Otherwise, you can just close the session. If you have any doubts, please type in. No doubts? Okay, okay. So that was all for today's session. So thank you for joining in. We will meet next time at the same time and discussing week 10 tutorial. Live problem session of week 10 tutorial. Thank you.